Welcome back to another journey through the cosmos of knowledge. Tonight, we're taking a different path. No dramatic revelations, no urgent discoveries demanding your attention. Just the gentle unfolding of scientific concepts, the quiet beauty of how the universe operates at its most fundamental levels. Think of this as a late-night conversation about the nature of reality itself, where understanding doesn't require urgency, only curiosity and the willingness to let ideas wash over you like waves on a distant shore. The fabric of reality. Everything you've ever experienced, every object you've touched, every breath you've taken exists within a framework so fundamental that we rarely stop to consider it. This framework is woven from threads we call space and time, energy and matter, forces that push and pull in an endless cosmic choreography. The universe operates on principles that are simultaneously elegant and complex, accessible yet profound. Consider for a moment the air surrounding you right now. It seems empty, featureless, yet it's teeming with molecules moving at hundreds of meters per second, colliding billions of times each second, transferring energy in an intricate dance of physics. These molecules obey laws that were discovered through centuries of careful observation, experimentation, and brilliant insights. The same laws that govern the air in your room also govern the formation of galaxies, the burning of stars, and the expansion of the universe itself. Physics emerged from humanity's attempt to understand patterns in nature. Ancient observers noticed that objects fall downward, that the sun rises and sets with remarkable regularity, that water flows from high places to low. These simple observations sparked questions that would echo through millennia. What makes things move? Why do they stop? What is the nature of matter itself? The quest for answers led to the development of scientific methods, ways of testing ideas against reality. Through experiment and mathematical description, patterns emerged. These patterns became principles, principles became laws, and laws wove together into theories that explain vast swaths of natural phenomena. The remarkable thing is how interconnected it all turns out to be. The force that makes an apple fall from a tree is the same force that keeps the moon in orbit around Earth. The energy that warms your skin in sunlight traveled millions of kilometers as electromagnetic waves, carrying with it information about nuclear reactions occurring in the sun's core. This interconnectedness reveals something profound about the universe. Despite its apparent complexity, despite the bewildering variety of phenomena we observe, the universe operates on a relatively small set of fundamental principles. These principles apply everywhere, from the quantum realm of subatomic particles to the cosmic scale of galactic superclusters. They apply now just as they did billions of years ago, and they'll continue to apply billions of years into the future. Understanding these principles doesn't diminish the wonder of existence. Instead, it deepens it. When you understand that the calcium in your bones was forged in the hearts of ancient stars, that the iron in your blood was created in supernova explosions, that the hydrogen atoms in your body have existed since the earliest moments of the universe, the interconnection between yourself and the cosmos becomes visceral and immediate. The scientific concepts we'll explore tonight aren't abstract, mathematical puzzles disconnected from everyday experience. They are the very foundation of that experience. The chair supporting you resists gravity through electromagnetic forces between atoms. The light allowing you to see comes from electrons changing energy states. The warmth you feel is the manifestation of molecular kinetic energy. Every sensation, every interaction is physics in action. What makes these concepts particularly suited for contemplation is their layered nature. On the surface, they can be understood intuitively. At deeper levels, they reveal mathematical structures of extraordinary beauty. You can appreciate the phenomenon of a wave without understanding partial differential equations. You can marvel at the behavior of light without grasping the full complexity of quantum electrodynamics. Science offers multiple entry points, multiple levels of understanding, each valid and valuable in its own way. Tonight's journey will take us through these concepts gently, allowing each idea to settle before moving to the next. We'll explore motion and energy, waves and fields, the nature of matter and the structure of spacetime. We'll venture into the quantum realm where particles behave in ways that defy classical intuition, and we'll touch on the relativistic domain where time itself becomes flexible. Throughout, we'll maintain a pace that invites contemplation rather than demanding concentration, allowing the beauty of these ideas to emerge naturally. The universe is vast beyond comprehension, yet its fundamental principles are accessible to anyone willing to ponder them. In that accessibility lies a profound democratization of wonder. You don't need specialized equipment or advanced degrees to appreciate the elegance of conservation laws, the symmetry of physical principles, or the deep connections between seemingly disparate phenomena. All you need is curiosity and patience. So settle in. Let your mind relax into a state of open receptiveness. We're about to explore the architecture of reality itself, the invisible scaffolding upon which all existence is built. These aren't just concepts to memorize and forget. They are lenses through which to view the world, perspectives that transform the ordinary into the extraordinary. A falling raindrop becomes a demonstration of gravitational acceleration. A rainbow becomes a display of light refraction and dispersion. The warmth of sunlight on your face becomes a tangible connection to nuclear fusion occurring 93 million miles away. The concepts themselves are timeless. They were true before humans existed to discover them, and they'll remain true long after humanity has vanished from the cosmic stage. Yet there's something deeply moving about the fact that the universe has evolved beings capable of understanding these principles, of looking out into the void and comprehending the rules by which it operates. We are, in a very real sense, the universe contemplating itself. As we move through these ideas, don't worry about remembering every detail. Instead, allow yourself to experience the interconnected nature of scientific understanding, the way each concept builds upon and relates to others, creating a coherent picture of how things work. Let the rhythm of explanation become a gentle current carrying you through landscapes of understanding, past familiar shores and into deeper waters where intuition gives way to mathematical beauty. The night is quiet. The universe continues its eternal dance, and we, for a brief moment, have the privilege of understanding a small part of that dance, of seeing the patterns underlying the apparent chaos, of recognizing the order within the complexity. It's a gift that science offers us, this ability to see deeper into the nature of things, to move beyond surface appearances and touch the fundamental principles that make existence possible. The dance of motion. Motion is perhaps the most intuitive of physical concepts, yet it conceals depths that took humanity centuries to fully understand. From your perspective right now, you might feel stationary at rest in whatever space you occupy. But that stillness is an illusion of scale and reference. In truth, you're in constant motion. The Earth rotates beneath you at roughly 1,670 kilometers per hour at the equator. It orbits the Sun at approximately 30 kilometers per second. The solar system itself moves through the galaxy, and the galaxy through the expanding universe. Motion is not the exception, but the rule, the fundamental state of matter in the cosmos. Understanding motion begins with understanding what we mean by position. Every object exists somewhere in space, and that somewhere can be described using coordinates, numbers that specify location relative to some chosen reference point. On a map, you might use latitude and longitude. In a room, you might use distances from the corners. In space, astronomers use elaborate coordinate systems tied to distant stars and galaxies. The key insight is that position is always relative. There's no absolute location in the universe, no cosmic signpost marking here in any fundamental sense. All positions are positions relative to something else. When an object's position changes with time, we say it's in motion. The rate of change of position defines velocity, one of the most important concepts in physics. Velocity tells us not just how fast something is moving, but also in what direction. This distinction matters profoundly. Two cars traveling at 60 kilometers per hour have the same speed, but if they are traveling in opposite directions, they have different velocities. Velocity is what physicists call a vector quantity, possessing both magnitude and direction. The natural state of objects, absent any forces acting upon them, is to continue moving at constant velocity. This principle, first clearly articulated by Galileo and later incorporated into Newton's laws of motion, contradicts our everyday intuition. When you roll a ball along the ground, it slows and stops. When you stop pedaling a bicycle, it coasts to a halt. These experiences suggest that objects naturally come to rest, that motion requires a constant cause to sustain it. But this intuition is misleading. The ball stops because friction between it and the ground removes energy from its motion. The bicycle slows because air resistance and friction in the wheel bearings oppose its motion. Remove these resistive forces, as astronauts did when they rolled objects across the airless surface of the moon, and objects in motion continue indefinitely. The natural state of matter is not rest, but uniform motion. Rest is simply the special case of zero velocity. When velocity changes, we encounter acceleration. Acceleration describes the rate at which velocity changes with time. If you're in a car and the driver presses the accelerator pedal, you feel yourself pushed back into your seat as the car's velocity increases. That sensation is your body's experience of acceleration. But acceleration doesn't only mean speeding up. It also encompasses slowing down, which physicists sometimes call deceleration or negative acceleration. And crucially, acceleration includes any change in direction, even if speed remains constant. Consider a car navigating a circular track at constant speed. Despite the unchanging speedometer reading, the car is accelerating because its direction is constantly changing. The acceleration points toward the center of the circle, perpendicular to the velocity. This centripetal acceleration is what keeps the car moving in a curve rather than flying off in a straight line. Without it, circular motion would be impossible. The connection between acceleration and force is fundamental. Newton's second law of motion states that force equals mass times acceleration. This deceptively simple equation encapsulates a profound truth. Forces cause changes in motion. The greater the force applied to an object, the greater its acceleration. The greater the object's mass, the smaller its acceleration for a given force. This is why you can easily accelerate a shopping cart, but find it much harder to accelerate a car, even though both roll on wheels. The car has vastly more mass, requiring a proportionally greater force to achieve the same acceleration. Mass itself is a fascinating concept, one that took centuries to fully disentangle from weight. Mass quantifies the amount of matter in an object, its resistance to changes in motion. Weight, by contrast, is the force exerted on that mass by gravity. Your mass remains constant whether you're on Earth, on the Moon, or floating in the depths of space. But your weight changes dramatically. On the Moon, with its weaker gravity, you'd weigh only about 1/6 of your Earth weight, even though your mass remained unchanged. In the weightlessness of orbit, you'd have no weight at all, yet your mass, and thus your inertia, would remain the same. It would still require force to accelerate your body to change its state of motion. Momentum emerges from the relationship between mass and velocity. Momentum is simply mass multiplied by velocity, representing the quantity of motion an object possesses. A massive truck moving slowly can have the same momentum as a small car moving quickly. This equivalence matters in collisions, where momentum is conserved. When two objects collide, the total momentum before the collision equals the total momentum after, though it may be redistributed between the objects. This conservation principle, one of the most fundamental in physics, allows us to analyze everything from billiard ball impacts to planetary formation, from subatomic particle collisions to galactic mergers. The concept of inertia underlies all of these ideas. Inertia is the tendency of objects to resist changes in their state of motion. An object at rest tends to remain at rest. An object in motion tends to continue in motion at constant velocity. This resistance to change is directly proportional to mass. More massive objects have greater inertia, requiring larger forces to achieve the same acceleration. You experience this whenever you try to stop a heavy object that's already moving, or when you attempt to change direction quickly while running. Forces come in many varieties, but they all share the common property of causing acceleration when applied to objects with mass. Gravity pulls objects toward massive bodies like Earth. Electromagnetic forces govern interactions between charged particles. Nuclear forces bind protons and neutrons together in atomic nuclei. Friction opposes relative motion between surfaces in contact. Each force has its characteristics, its range of influence, its mathematical description. Yet all forces ultimately do the same thing. They change the motion of objects they act upon. Newton's third law introduces another crucial principle. For every action, there's an equal and opposite reaction. When you push against a wall, the wall pushes back against you with equal force. When a rocket expels exhaust gases downward, those gases exert an equal upward force on the rocket. This reciprocity is absolute and universal. Forces always come in pairs, acting on different objects but equal in magnitude and opposite in direction. Understanding motion also requires understanding frames of reference. The laws of physics work the same way in all inertial reference frames, meaning all frames moving at constant velocity relative to each other. If you're in a smoothly moving train, you can play catch with a ball exactly as you would on the ground. The ball doesn't know that the train is moving. From your perspective inside the train, the laws of motion work identically to how they work for someone standing still on a platform. Only when the train accelerates, braking or turning, do you notice any difference. Acceleration is absolute in a way that velocity is not. This principle of relativity, understood by Galileo long before Einstein expanded it, tells us something profound about the universe. There's no preferred state of motion, no cosmic reference frame that counts as absolutely at rest. All motion is relative to something else. The Earth moves relative to the Sun relative to the galactic center, the galaxy relative to others in our local group. But none of these motions is more fundamental than any other. Each reference frame is equally valid for describing physical laws. Rotational motion adds another layer of complexity and beauty. When objects spin or orbit, they possess angular momentum, the rotational equivalent of linear momentum. Like its linear counterpart, angular momentum is conserved in closed systems. A figure skater spinning with arms extended rotates relatively slowly. When the skater pulls their arms in, reducing their moment of inertia, they spin faster. The total angular momentum remains constant, but its distribution changes, illustrating one of physics's most elegant principles. Torque relates to rotational motion, as force relates to linear motion. Torque is the rotational equivalent of force, the influence that causes objects to rotate or changes their rate of rotation. When you turn a doorknob, you apply torque. When you use a wrench to tighten a bolt, you apply torque. The magnitude of torque depends not only on the force applied but also on where and how it's applied. Pushing near the edge of a door is more effective than pushing near the hinges because the torque increases with distance from the axis of rotation. Motion pervades everything. At the molecular level, the temperature of a substance reflects the average kinetic energy of its constituent particles. In a gas, molecules zip around at hundreds of meters per second, colliding constantly. In a solid, atoms vibrate about fixed positions, their motion constrained but never absent. Even at absolute zero, the lowest theoretically possible temperature, quantum mechanics tells us that particles retain some zero-point motion. Perfect stillness is impossible in a quantum universe. The study of motion extends from the everyday to the cosmic. Projectile motion describes the parabolic paths of thrown objects, combining horizontal motion at constant velocity with vertical motion under constant gravitational acceleration. Orbital mechanics, building on the same principles, explains how planets circle stars and moons circle planets. The International Space Station doesn't stay in orbit because it's beyond Earth's gravity. It stays in orbit because it's continuously falling toward Earth while also moving forward fast enough that its trajectory curves around the planet rather than intersecting its surface. Orbit is perpetual free fall, a delicate balance between gravitational attraction and tangential velocity. Understanding motion transformed human civilization. It enabled us to build machines that amplify our physical capabilities, to navigate across oceans and through the air, eventually to escape Earth's gravitational embrace and set foot on other worlds. Every bridge, every vehicle, every rotating machine embodies principles of motion discovered through careful observation and mathematical analysis. The same equations that describe a ball rolling down a hill also describe the motion of electrons in an atom, scaled appropriately and sometimes modified by quantum or relativistic effects. As we move through our lives, we unconsciously apply our intuitive understanding of motion. We catch thrown objects by predicting their trajectories. We navigate through crowds by estimating velocities and adjusting our own. We sense acceleration in vehicles and compensate with our balance. This intuitive physics, developed through experience, works remarkably well for the scales and speeds of everyday life. It's only when we venture into extremes, very fast or very slow, very large or very small, that our intuition fails us and we need the full mathematical apparatus of physics to guide us. The mathematics of motion can become quite sophisticated, involving calculus and differential equations, vector spaces, and tensor calculus. But the core ideas remain accessible. Position changes to give velocity. Velocity changes to give acceleration. Acceleration requires force. Mass resists acceleration. Momentum and angular momentum are conserved. These principles, properly understood, unlock the door to understanding virtually all mechanical phenomena, from the swing of a pendulum to the precession of planetary orbits, from the rotation of galaxies to the vibration of atoms. Energy's many faces. Energy might be the most fundamental concept in all of physics, yet it's also one of the most elusive to define precisely. We use the word constantly in everyday conversation. We talk about having energy or lacking it, about energy efficiency and energy consumption. But what is energy really? At its core, energy is the capacity to do work, to cause change, to make things happen. It's a quantity that can take many forms, can be transferred from one system to another, can be transformed from one type to another, but can never be created or destroyed. This last statement, the principle of conservation of energy, ranks among the most important discoveries in the history of science. Consider a ball held above the ground. It possesses gravitational potential energy by virtue of its position in Earth's gravitational field. Release the ball, and this potential energy converts to kinetic energy, the energy of motion. As the ball falls, it accelerates, gaining speed, its kinetic energy increasing as its potential energy decreases. At the instant before impact, nearly all the original potential energy has transformed into kinetic energy. Then comes the collision with the ground. The kinetic energy doesn't vanish. It spreads out, transforming into sound waves, thermal energy from friction and deformation, perhaps elastic energy if the ball bounces. Account for all these forms, and the total energy remains constant. None was created, none destroyed, only transformed and redistributed. Kinetic energy depends on mass and velocity. Specifically, it equals 1/2 the mass times the velocity squared. The dependence on velocity squared has profound implications. Double an object's velocity, and its kinetic energy quadruples. This is why car crashes become so much more dangerous at higher speeds. It's why asteroid impacts can be so devastating. A small asteroid moving at tens of kilometers per second carries tremendous kinetic energy, which converts catastrophically into thermal energy and mechanical deformation upon impact. Potential energy comes in many varieties. Gravitational potential energy, as we've discussed, depends on an object's position in a gravitational field. Elastic potential energy is stored in compressed springs, stretched rubber bands, bent tree branches. Chemical potential energy resides in the bonds between atoms, released in chemical reactions like combustion or digestion. Electrical potential energy exists in charged particles separated by distance, ready to flow when a conductive path connects them. Nuclear potential energy dwells in atomic nuclei, unleashed in nuclear reactions or the sun's core. The work-energy theorem establishes a crucial connection. Work, in physics, means force applied through distance. When you push a box across a floor, you do work on it. The amount of work equals the force times the distance moved in the direction of the force. The work-energy theorem states that the net work done on an object equals its change in kinetic energy. Push a stationary box and it speeds up, gaining kinetic energy equal to the work you performed. Friction does negative work, removing kinetic energy and converting it to thermal energy. Power quantifies the rate of energy transfer or transformation. A 100-watt light bulb converts electrical energy to light and heat at a rate of 100 joules per second. A 1,000-watt microwave oven delivers energy to your food at 10 times that rate. Power matters in practical applications because faster energy transfer often means greater capability. A high-power engine can accelerate a car more quickly than a low-power one. A high-power laser can cut through metal, while a low-power laser pointer merely illuminates a spot. Energy conservation doesn't mean energy is static. It flows constantly, transforming, transferring, cascading from one form to another in an endless cosmic metabolism. Sunlight carries energy from nuclear fusion in the sun's core. Plants capture some of this energy through photosynthesis, converting it to chemical energy stored in sugars and starches. Animals eat plants or each other, breaking down these molecules and releasing the stored energy to power their metabolism. Eventually, all this energy dissipates as low-grade thermal energy, radiating into the environment, increasing entropy but never actually vanishing. Thermodynamics gives us formal laws governing energy and entropy. The first law of thermodynamics is essentially the conservation of energy stated for thermodynamic systems. Energy can enter or leave a system as heat or work, but the total energy of system plus surroundings remains constant. The second law introduces entropy, a measure of disorder or the unavailability of energy to do work. In any natural process, the total entropy of a closed system increases. This is why engines can never be perfectly efficient, why heat flows from hot to cold but not the reverse without external work, why the universe trends toward equilibrium. The concept of temperature connects intimately with energy. Temperature measures the average kinetic energy of particles in a substance. In a hot gas, molecules move rapidly, carrying substantial kinetic energy. In a cold solid, atoms vibrate more slowly about their lattice positions. At absolute zero, theoretically the lowest possible temperature, classical physics would predict that all thermal motion ceases. Quantum mechanics modifies this picture slightly, requiring some residual zero-point energy even at absolute zero, but the basic principle holds. Temperature reflects microscopic kinetic energy. Heat differs from temperature, though the two are related. Heat is energy in transit, flowing from regions of higher temperature to regions of lower temperature. When you touch a hot stove, thermal energy flows into your hand, and you perceive this flow as heat. The stove doesn't contain heat, it contains thermal energy. Heat is what we call that energy when it's moving from one system to another because of a temperature difference. Energy density matters in practical applications. Gasoline stores about 32 megajoules per liter, which explains why it's such an effective fuel for vehicles. Batteries store much less energy per unit mass or volume, which is why electric cars need large battery packs to achieve practical driving ranges. Nuclear fuels have extraordinary energy density, millions of times greater than chemical fuels, deriving from the much stronger forces binding atomic nuclei compared to the electromagnetic forces binding molecules. The famous equation E equals mc squared, Einstein's most recognized formula, reveals that mass itself is a form of energy. The c in the equation represents the speed of light, an enormous number, and it's squared, making it even more enormous. This means that even tiny amounts of mass contain staggering amounts of energy. A single kilogram of matter, if completely converted to energy, would release about 90 petajoules, equivalent to 21 megatons of TNT. This is why nuclear reactions, which convert tiny fractions of mass to energy, release so much more energy than chemical reactions, which merely rearrange atoms without changing their mass appreciably. Energy manifests in electromagnetic radiation, in photons of light-carrying energy proportional to their frequency. High-frequency ultraviolet photons carry more energy than low-frequency infrared photons, which is why UV radiation can damage biological molecules while infrared merely warms them. The full electromagnetic spectrum, from radio waves through visible light to gamma rays, represents energy in electromagnetic form, with photon energies spanning many orders of magnitude. Sound waves carry energy through mechanical vibration of matter. The louder the sound, the more energy the wave carries. Very loud sounds can physically damage structures or hearing precisely because they transport significant energy. Earthquake waves are essentially very low-frequency sound waves in rock, carrying enormous energy released by tectonic motion. These seismic waves can travel thousands of kilometers through Earth's interior, detectable on the opposite side of the planet. Energy considerations govern chemical reactions. Exothermic reactions release energy, usually as heat, when product molecules have lower potential energy than reactant molecules. Combustion of fuels is exothermic, which is why it produces heat and makes engines work. Endothermic reactions absorb energy, requiring an input of heat or light. Photosynthesis is endothermic, using sunlight to to drive energetically unfavorable reactions that build complex molecules from simpler ones. Living systems are intricate energy processors. We consume food containing chemical potential energy. Our cells break down these molecules through metabolic pathways, capturing some of the released energy in ATP, the cell's energy currency. This ATP powers all the work of living: muscle contraction, nerve signal propagation, molecule synthesis, active transport across membranes. Eventually, the energy dissipates as heat, maintaining our body temperature and radiating into our environment. We are, in a thermodynamic sense, complex patterns maintained far from equilibrium by a constant flow of energy. Energy scales span an almost incomprehensible range. A single photon of visible light carries about 4 times 10 to the negative 19 joules, a vanishingly small amount. A lightning bolt releases roughly 1 billion joules. The sun produces about 4 times 10 to the 26th watts, or 400 quadrillion watts, every second. The total energy content of the observable universe, including the mass energy of all matter and the energy in electromagnetic radiation, is estimated at about 10 to the 69th joules, though this number has large uncertainties. Understanding energy transforms how we see the world. A growing plant is a machine that captures solar energy and stores it in chemical bonds. A thunderstorm is an energy converter, transforming solar energy that evaporated water and created air mass differences into the kinetic energy of wind and the electrical energy of lightning. Your beating heart is a pump powered by chemical energy from food, converted through many steps into the mechanical work of blood circulation. Energy efficiency becomes a practical concern precisely because while energy is conserved, useful energy isn't. Every energy transformation involves some loss to forms we can't easily recover or use. A car engine converts only about 20 to 30% of gasoline's chemical energy to useful mechanical work. The rest becomes waste heat. Power plants, electric motors, light bulbs, all operate below perfect efficiency. The second law of thermodynamics guarantees that perfect efficiency is impossible. Some energy always becomes unavailable for useful work, increasing entropy, spreading out into forms from which it can't be recovered. The human quest for energy sources has shaped civilization. Fire gave us access to chemical energy in wood. Water wheels and windmills captured kinetic energy from flowing water and moving air. Steam engines liberated us from location-dependent energy sources by burning coal or wood anywhere. Internal combustion engines provided portable, powerful energy conversion. Nuclear reactors tap the binding energy of atomic nuclei. Solar panels directly convert electromagnetic energy from the sun to electrical energy. Each advance in harnessing and converting energy enabled new capabilities, new forms of organization, new ways of living. Energy considerations explain astronomical phenomena. Stars shine because nuclear fusion in their cores converts mass to energy, releasing photons that eventually escape the stellar surface and illuminate the cosmos. Supernova occur when massive stars exhaust their nuclear fuel and collapse, releasing in seconds as much energy as the sun will produce in its entire 10 billion-year lifetime. Quasars shine more brightly than 1 trillion suns, powered by matter falling into supermassive black holes, converting gravitational potential energy to electromagnetic radiation with astonishing efficiency. The warmth of existence. Temperature and heat form an experiential bridge between the human scale world and the molecular realm. You know immediately what it means for something to be hot or cold. You felt the warmth of sunlight on your skin, the chill of winter air, the searing pain of touching something too hot. These everyday experiences reflect deep physical principles governing energy distribution at the atomic level. At the microscopic scale, temperature is motion. In a gas, temperature measures the average kinetic energy of molecules careening through space, colliding billions of times per second. In a solid, temperature reflects the vigor of atomic vibrations about equilibrium positions in the crystal lattice. Higher temperature means more energetic motion, faster vibrations, more violent collisions. Lower temperature means calmer, gentler motion. Absolute zero, the theoretically lowest possible temperature, would represent the state of minimal motion, though quantum mechanics requires some residual zero-point energy even then. Heat is energy in transit. It flows spontaneously from hotter regions to cooler ones, never the reverse without external intervention. This asymmetry, this preferred direction of heat flow, is a manifestation of the second law of thermodynamics, one of the most profound principles in physics. The law states that entropy, a measure of disorder, always increases in closed systems. Heat flowing from hot to cold represents energy spreading out, becoming more evenly distributed, increasing the universe's entropy. Three mechanisms transport heat through matter and space. Conduction transfers thermal energy through direct contact as faster-moving atoms or molecules collide with slower-moving neighbors, gradually spreading the energy. Metal feels cold to the touch partly because it's an excellent conductor, rapidly drawing heat away from your warm skin. Wood, a poor conductor, feels warmer because it removes heat from your skin much more slowly. Convection moves heat through bulk motion of fluids. Warm air rises because it's less dense than cooler air, creating convection currents that distribute heat throughout a room. Ocean currents are giant convection cells that transport tremendous amounts of thermal energy across the planet, strongly influencing climate. The mantle beneath Earth's crust convects over geological timescales, driving plate tectonics and volcanic activity. Radiation transfers energy without requiring any material medium. The sun warms Earth across 93 million miles of near vacuum because thermal radiation doesn't need atoms to carry it. All objects with temperature above absolute zero emit electromagnetic radiation, with the peak wavelength depending on temperature. Hot objects glow visibly. Cooler objects emit infrared radiation, invisible to our eyes but detectable with thermal cameras or felt as warmth without contact. The relationship between heat and work, central to thermodynamics, drove the Industrial Revolution and shaped modern technology. Early steam engines converted heat from burning fuel into mechanical work, though inefficiently. Understanding why this inefficiency is inevitable led to deep insights about entropy and the fundamental limits on energy conversion. The first law of thermodynamics expresses energy conservation for systems that can exchange heat and work with their surroundings. The change in a system's internal energy equals the heat added to it minus the work done by it. This deceptively simple bookkeeping underlies all thermal analysis, from engine design to climate modeling. The second law introduces entropy, declaring that in any natural process involving an isolated system, entropy never decreases. This law explains why processes have a direction, why some things happen spontaneously while their reverse never does. Ice cubes melt in warm water, but the reverse never occurs spontaneously. Perfume released in a corner of a room diffuses throughout the space, but never spontaneously reconcentrates. Gases expand to fill their containers, but never spontaneously compress themselves into smaller volumes. Entropy can decrease locally if energy is supplied from elsewhere. Your refrigerator decreases the entropy of its interior by pumping heat out, but this requires work from the compressor, and the overall entropy of refrigerator plus surroundings increases. Living organisms maintain their remarkably low entropy structures by consuming food and radiating waste heat, increasing the universe's entropy even as they temporarily decrease their own. temperature scales quantify our thermal experience. The Celsius scale sets 0 at water's freezing point and 100 at its boiling point, convenient reference points at sea level. The Fahrenheit scale, still used in the United States, sets different arbitrary reference points. The Kelvin scale, preferred in science, sets 0 at absolute zero, making temperature directly proportional to average molecular kinetic energy. The difference is just a scale shift. The Celsius, degree, and the Kelvin are the same size, so temperature differences are the same in both systems. Specific heat capacity describes how much energy is needed to change a substance's temperature. Water has an unusually high specific heat, meaning it takes considerable energy to change its temperature. This property moderates Earth's climate as oceans store and release enormous amounts of thermal energy with relatively small temperature changes. It also explains why coastal regions have milder climates than interior regions at similar latitudes. The ocean acts as a thermal buffer. Phase transitions occur when matter changes state from solid to liquid, liquid to gas, or the reverse. These transitions require or release latent heat, energy that goes into breaking molecular bonds rather than increasing temperature. When ice melts, it absorbs heat without changing temperature until the phase transition completes. When water boils, it absorbs heat at constant temperature. This latent heat is why steam burns are often more severe than water burns at the same temperature. The steam releases additional energy as it condenses on skin. The concept of thermal equilibrium underlies temperature measurement. Two systems in thermal contact exchange energy until they reach the same temperature, at which point net heat flow ceases. A thermometer works by coming into thermal equilibrium with whatever it's measuring. The expansion of mercury or alcohol in traditional thermometers, the electrical resistance of thermistors, the infrared emission detected by non-contact thermometers, all provide ways to measure temperature by detecting thermal equilibrium conditions. Molecular motion at human body temperature is vigorous. Nitrogen and oxygen molecules in the air around you jet about at average speeds around 500 meters per second. In your body, molecules engage in constant thermal dance, colliding, vibrating, rotating. Your body temperature of approximately 37 degrees Celsius isn't some arbitrary value. It's the temperature at which biochemical reactions proceed at rates optimal for life, fast enough for efficiency but not so fast that molecules damage themselves through over-energetic collisions. The atmosphere's temperature structure tells a story of energy absorption and transport. Near the surface, temperature typically decreases with altitude as pressure drops and air expands, cooling adiabatically. In the stratosphere, temperature increases with altitude because ozone absorbs ultraviolet radiation, heating the surrounding air. These temperature variations drive winds and weather patterns, ultimately powered by uneven solar heating between equator and poles. Thermal expansion explains everyday phenomena from thermometers to thermostats. Most materials expand when heated as increased molecular motion pushes atoms slightly farther apart. This principle allows metal thermometers to work, causes bridges to need expansion joints, makes hot air balloons rise. Water is unusual, contracting as it cools until 4 degrees Celsius, then expanding as it freezes. This anomaly is why ice floats, why lakes freeze from the top down, preserving life beneath the ice through winter. The greenhouse effect, crucial to understanding climate, is fundamentally about thermal radiation. Earth's surface, warmed by visible sunlight, emits infrared radiation. Certain gases in the atmosphere, particularly carbon dioxide and water vapor, absorb infrared strongly while being transparent to visible light. They trap outgoing radiation, re-emitting some back toward the surface. This elevates Earth's surface temperature above what it would be with no atmosphere. The effect is named for greenhouses, though the mechanisms differ. Greenhouses trap warm air, while the atmospheric greenhouse effect traps radiation. Heat engines convert thermal energy to mechanical work, but with fundamental limitations. The Carnot cycle represents the theoretical maximum efficiency, determined solely by the temperatures of hot and cold reservoirs. Real engines operate below this maximum because of friction, heat leaks, and practical constraints. Understanding these limits guided engineering advances from steam locomotives to modern gas turbines, each design seeking to approach closer to theoretical efficiency. Refrigerators and heat pumps are engines run backward, using work to move heat from cold to hot. A refrigerator pumps heat from its cold interior to the warmer room. A heat pump moves heat from cold outdoor air to warm interior space. Both seem to violate the natural direction of heat flow, but they require work input, and the total entropy of system plus surroundings still increases. Statistical mechanics provides the bridge between microscopic motion and macroscopic temperature. Individual molecules follow deterministic laws, but tracking 10 to the 23rd of them is impossible. Instead, statistical methods predict average behaviors. Temperature emerges as the average kinetic energy. Pressure arises from countless molecular impacts on container walls. Entropy relates to the number of microscopic states consistent with macroscopic observables. This statistical view unified thermodynamics with mechanics, revealing that thermal phenomena emerge from the collective behavior of enormous numbers of particles. The third law of thermodynamics states that entropy approaches zero as temperature approaches absolute zero. Perfect crystals at absolute zero would have only one possible microscopic arrangement, giving zero entropy. This law implies that absolute zero is unattainable in finite steps, though laboratory techniques have achieved temperatures within billionths of a Kelvin above absolute zero, cold enough for exotic quantum phenomena like Bose-Einstein condensation to occur. Thermal physics governs stellar evolution. Stars balance gravitational collapse against thermal pressure from nuclear fusion. As hydrogen fuel depletes, stars undergo dramatic changes. Massive stars fuse increasingly heavy elements, each stage releasing less energy, until iron forms in the core. Iron fusion consumes rather than releases energy. Without thermal support, the core collapses catastrophically, triggering a supernova explosion that scatters heavy elements through space, enriching the interstellar medium from which new stars and planets form. The cosmic microwave background, discovered in 1965, is thermal radiation left over from the Big Bang. Originally intensely hot, this radiation has cooled through cosmic expansion to a mere 2.7 Kelvin above absolute zero. Its near-perfect blackbody spectrum and tiny temperature variations across the sky provide our most direct view of the early universe, confirming predictions of Big Bang cosmology and constraining models of cosmic evolution. Waves that shape our world. Waves are patterns of disturbance that propagate through space and time, carrying energy and information without transporting matter over long distances. They are so fundamental to physics that they appear in virtually every domain, from water waves you can watch on a pond to quantum mechanical waves describing particles, from seismic waves shaking Earth during earthquakes to gravitational waves rippling through spacetime itself. The defining characteristics of waves include wavelength, the distance between successive crests or equivalent points, frequency, the number of complete cycles passing a point per unit time, amplitude, the maximum disturbance from equilibrium, and speed, how fast the wave pattern moves through its medium. These properties relate through the simple equation that wave speed equals wavelength times frequency. Double the frequency while maintaining speed, and wavelength halves. Waves divide into two categories based on the direction of disturbance relative to propagation. In transverse waves, the disturbance moves perpendicular to wave propagation. Light waves are transverse, with electric and magnetic fields oscillating perpendicular to the direction of travel. Waves on a string, where the string moves up and down while the wave moves horizontally, are transverse. In longitudinal waves, the disturbance moves parallel to propagation. Sound waves are longitudinal, consisting of compressions and rarefactions of the medium moving in the same direction the sound travels. Superposition is a fundamental wave property. When two waves meet, they add together, creating a combined disturbance equal to the sum of individual disturbances. This leads to interference patterns. Constructive interference occurs when waves align so crests meet crests and troughs meet troughs, producing larger amplitude. Destructive interference occurs when crests meet troughs, reducing or canceling amplitude. The iridescent colors in soap bubbles result from interference between light waves reflected from front and back surfaces of the thin film. Standing waves form when waves interfere with their own reflections in confined spaces. Musical instruments exploit standing waves. A guitar string vibrates in patterns where certain points, called nodes, remain stationary while other points, antinodes, oscillate with maximum amplitude. The fundamental frequency corresponds to the simplest standing wave pattern. Higher harmonics involve more nodes and antinodes. The sound you hear combines the fundamental with various harmonics, giving each instrument its distinctive timbre. Resonance occurs when a system is driven at a frequency matching its natural frequency of oscillation. The amplitude can grow dramatically large, sometimes destructively so. A well-known historical example is the Tacoma Narrows Bridge collapse in 1940. Though engineers now understand the mechanism was more complex than simple resonance, involving aeroelastic flutter where wind-driven oscillations fed back into the structure's motion. This highlighted the importance of understanding dynamic responses in design. On the beneficial side, radio receivers use resonance. Tuning adjusts a circuit's natural frequency to match the desired station's broadcast frequency, causing that signal to resonate and be detected while others remain weak. Sound waves are mechanical pressure waves requiring a medium. In air, sound travels about 343 meters per second at room temperature, much slower than light, which explains why you see lightning before hearing thunder. Sound speed increases with temperature and varies with medium. Sound travels faster in water and much faster still in solids because particles are closer together, allowing disturbances to propagate more quickly. The Doppler effect describes how observed frequency changes when source or observer moves. When a sound source approaches, emitted waves bunch together, increasing frequency and pitch. When it recedes, waves spread out, decreasing frequency. You hear this as the pitch drop of a passing ambulance siren. The Doppler effect works for any wave type, including light. Astronomers use it to measure stellar velocities and discovered that distant galaxies are redshifted, meaning they are moving away, leading to the realization that the universe expands. Diffraction occurs when waves encounter obstacles or openings. Instead of traveling in straight lines, waves bend around corners and spread through apertures. The amount of diffraction depends on wavelength relative to obstacle size. Long wavelength radio waves easily diffract around buildings, which is why you can receive AM radio signals even without line of sight to the transmitter. Short wavelength light diffracts much less, producing shadows with relatively sharp edges, though careful examination reveals diffraction fringes at shadow boundaries. Reflection happens when waves encounter a boundary and bounce back. Smooth surfaces produce specular reflection, where angle of incidence equals angle of reflection, like a mirror. Rough surfaces produce diffuse reflection, scattering waves in many directions, which is why most objects don't appear mirror-like even though they reflect plenty of light. Echoes are reflected sound waves. Sonar and radar use reflection of sound and radio waves to detect and locate objects. Refraction bends waves at boundaries between different media where wave speed changes. Light slows when entering glass or water, bending toward the normal to the surface. This explains why objects underwater appear closer than they are, why lenses can focus light, and why the atmosphere refracts sunlight, allowing you to see the sun even after it's geometrically below the horizon. Seismic waves from earthquakes come in two main types. Primary waves, or P waves, are longitudinal compression waves that travel through both solid and liquid rock. Secondary waves, or S waves, are transverse shear waves that propagate only through solids. The different arrival times of P waves and S waves at seismographs allow geologists to triangulate earthquake locations. The inability of S waves to pass through Earth's core provided evidence that the outer core is liquid. Ocean waves are complex, involving both transverse and longitudinal motion. Water particles move in roughly circular paths as waves pass. In deep water, waves travel at speeds depending on wavelength. Longer waves move faster. As waves approach shore and encounter shallower water, their speed decreases, wavelength shortens, and amplitude increases until waves become unstable and break. The steady crashing of surf represents continuous energy transfer from wind to waves to shore. Electromagnetic waves require no medium, propagating through vacuum at the speed of light. They span an enormous spectrum from low-frequency radio waves with wavelengths of kilometers to high-frequency gamma rays with wavelengths shorter than atomic nuclei. All electromagnetic waves travel at the same speed in vacuum, about 300,000 kilometers per second, but differ in wavelength and frequency. The spectrum includes radio, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays in order of increasing frequency and energy. Visible light occupies a tiny slice of the electromagnetic spectrum, roughly 400 to 700 nanometers wavelength. Different wavelengths within this range correspond to different colors, from violet at the short end through blue, green, yellow, and orange to red at the long end. White light contains all visible wavelengths mixed together. A prism separates white light into its component colors because glass refracts different wavelengths by different amounts, a phenomenon called dispersion. Light exhibits both wave and particle properties, an instance of wave-particle duality fundamental to quantum mechanics. In some experiments, like the double-slit experiment, light behaves unmistakably as waves, creating interference patterns. In others, like the photoelectric effect, light behaves as particles called photons, discrete packets of energy. This duality isn't limited to light. All matter exhibits wave properties at quantum scales, though these become significant only for very small objects like electrons. The wave nature of matter, proposed by Louis de Broglie, associates a wavelength with any moving particle inversely proportional to its momentum. For everyday objects, this wavelength is so small as to be utterly negligible. For electrons, it's large enough to produce observable effects. Electron microscopes exploit electron waves to achieve much higher resolution than light microscopes because electron wavelengths are much shorter than visible light wavelengths. Quantum mechanics describes particles using wave functions, mathematical objects that encode probability amplitudes. The wave function's magnitude squared gives the probability of finding the particle at various locations. This interpretation, developed primarily by Max Born and the Copenhagen School, replaces deterministic trajectories with probabilistic predictions. The wave function evolves deterministically according to Schrödinger's equation, but measurement causes it to collapse randomly to one of many possible outcomes, with probabilities determined by the wave function before measurement. The uncertainty principle, discovered by Werner Heisenberg, states that certain pairs of properties, like position and momentum, can't simultaneously have definite values. The more precisely you know position, the less precisely you can know momentum, and vice versa. This isn't a technological limitation, but a fundamental feature of quantum reality, deeply connected to wave-particle duality. Waves are inherently spread out, so a particle described by a wave function can't have both perfectly definite position and perfectly definite momentum. The electric universe. Electricity and magnetism, once thought to be separate phenomena, reveal themselves as two aspects of a single fundamental interaction, electromagnetism. This unification, achieved primarily through the work of James Clerk Maxwell in the 1860s, ranks among the great intellectual achievements of physics. Understanding electromagnetism opens windows into phenomena ranging from chemical bonds that hold molecules together to the light that illuminates the universe. Electric charge is a fundamental property of matter, coming in two types arbitrarily called positive and negative. Like charges repel, opposite charges attract. This simple rule governs an astonishing variety of phenomena. Protons carry positive charge. Electrons carry negative charge, equal in magnitude but opposite in sign to the proton charge. Neutrons are electrically neutral. Most matter is electrically neutral overall because it contains equal numbers of protons and electrons, but charge can be separated, creating charged objects. Rubbing certain materials together transfers electrons from one to the other, leaving one negatively charged and the other positively charged. This triboelectric effect creates the static electricity that makes your hair stand up after combing, that causes a shock when you touch metal after walking on carpet, that makes clothes cling out of the dryer. The charged objects exert forces on each other and on neutral objects. A charged balloon sticks to a wall because it induces opposite charges on the wall's surface, creating attraction. Coulomb's law quantifies the electric force between charged objects. The force is proportional to the product of the charges and inversely proportional to the square of the distance between them. This inverse square law has the same form as Newton's law of gravitation, though electromagnetism is vastly stronger than gravity. The electric repulsion between two protons is about 10 to the 36 times stronger than their gravitational attraction. Gravity dominates at large scales only because matter is typically electrically neutral, while gravitational mass comes only in one sign, always attractive. The electric field concept introduced by Michael Faraday provides a powerful way to think about electric forces. A charged object creates an electric field in the space around it. Other charges experience forces in this field. The field exists whether or not test charges are present to experience it. Field lines visualize the field. Pointing in the direction a positive charge would be pushed, with density indicating field strength. From a positive charge, field lines radiate outward. Around a negative charge, they point inward. Electric potential, often called voltage, measures electrical potential energy per unit charge. It's the electrical analog of gravitational potential energy. Just as objects naturally move from higher to lower gravitational potential, charges naturally move from higher to lower electric potential. Potential difference drives electric current through conductors. A battery maintains a potential difference between its terminals, creating an electric field in connected wires that pushes electrons, constituting an electric current. Current is the flow of charge, measured in amperes. 1 ampere equals 1 coulomb of charge flowing past a point per second. In metal wires, current consists of electrons drifting through the conductor, though by historical convention current direction is defined as the direction positive charges would flow, opposite to electron motion. In solutions, both positive and negative ions can carry current. In plasma, both electrons and positive ions contribute. Resistance opposes current flow arising from collisions between moving charges and atoms in the conductor. Ohm's law states that current equals voltage divided by resistance. For a given voltage, higher resistance means less current. Resistance depends on material properties and geometry. Good conductors like copper have low resistance. Insulators like rubber have extremely high resistance. Superconductors, materials cooled below critical temperatures, have zero resistance, allowing current to flow indefinitely without voltage applied. Electrical circuits allow us to control and utilize electric current. A simple circuit might include a battery providing voltage, wires conducting current, and a resistor, such as a light bulb, that converts electrical energy to other forms. More complex circuits include capacitors that store charge, inductors that store energy in magnetic fields, and transistors that switch or amplify signals. All modern electronics, from smartphones to supercomputers, are ultimately just very sophisticated electrical circuits. Magnetism arises from moving charges. A straight current-carrying wire creates a circular magnetic field around it. A coil of wire carrying current acts as a magnet with north and south poles. Permanent magnets derive their magnetism from aligned electron spins within the material, essentially tiny circulating currents at the atomic scale. Earth itself is a giant magnet, probably due to currents in the liquid iron outer core, though the detailed mechanism remains debated. Magnetic fields exert forces on moving charges perpendicular to both the charge's velocity and the field direction. This causes charged particles to follow curved paths in magnetic fields. Cosmic rays, high-energy charged particles from space, spiral along Earth's magnetic field lines, concentrating near the poles where they collide with atmospheric molecules, creating auroras. Particle accelerators use magnetic fields to steer beams around circular paths. Magnetic resonance imaging uses magnetic fields to manipulate atomic nuclei in the body, producing detailed medical images. Electromagnetic induction, discovered by Michael Faraday, occurs when changing magnetic fields create electric fields, inducing voltages and driving currents. A magnet moved through a coil of wire generates current in the coil. This principle underlies electric generators. Mechanical energy rotates coils in magnetic fields, inducing currents that provide electric power. The reverse process, using electric current to produce motion, powers electric motors. Maxwell's equations, four mathematical expressions, completely describe classical electromagnetism. They relate electric and magnetic fields to their sources, charges, and currents, and to each other. One equation says electric charges produce electric fields. Another says magnetic field lines always form closed loops, magnetic monopoles don't exist. A third is Faraday's law of induction. The fourth, Ampere's law with Maxwell's correction, says electric currents and changing electric fields produce magnetic fields. Maxwell realized his equations predicted waves, coupled oscillating electric and magnetic fields propagating through space. Calculating their speed using constants from electrical and magnetic measurements, he found it equaled the speed of light. This led him to propose that light is an electromagnetic wave, a revolutionary idea that unified optics with electromagnetism. Later experiments confirmed electromagnetic waves at many frequencies, from radio to gamma rays, all traveling at light speed in vacuum. Radio communication exploits electromagnetic waves. An oscillating current in an antenna produces electromagnetic waves that propagate outward. A receiving antenna some distance away experiences oscillating electric fields from the passing wave, inducing oscillating currents that can be amplified and converted to sound or data. Modern telecommunications, including radio, television, cell phones, Wi-Fi, and satellite communications, all use electromagnetic waves of various frequencies. The electromagnetic spectrum spans many orders of magnitude. Radio waves have wavelengths from millimeters to kilometers, frequencies from kilohertz to gigahertz. Microwaves, with wavelengths from about a millimeter to 30 centimeters, are used in radar and microwave ovens. Infrared, with wavelengths from roughly 700 nanometers to a millimeter, is felt as radiant heat. Visible light occupies 400 to 700 nanometers. Ultraviolet, from 10 to 400 nanometers, can damage biological molecules. X-rays and gamma rays, with wavelengths shorter than 10 nanometers, penetrate matter and carry sufficient energy to ionize atoms. Electromagnetic forces bind atoms into molecules, hold solids together, and govern all of chemistry. When atoms approach, their electron clouds interact electromagnetically. Attractive forces dominate at moderate distances, allowing chemical bonds to form. At very short distances, repulsion dominates as electron clouds overlap, preventing atoms from collapsing into each other. The balance between attraction and repulsion determines bond lengths and strengths, molecular geometries, and material properties. From a certain perspective, almost everything in daily life is electromagnetic. Contact forces when you touch something arise from electromagnetic repulsion between electron clouds. Friction, tension, compression, all fundamentally electromagnetic. Light allowing vision is electromagnetic. The chemical energy powering life stores and releases electromagnetic potential energy. Only gravity, the weak and strong nuclear forces, and quantum mechanical effects fall outside electromagnetism's domain, and even quantum mechanics heavily features electromagnetic interactions. When reality bends, Einstein's theories of relativity revolutionized our understanding of space-time and gravity. Special relativity, published in 1905, revealed that space and time are not absolute but depend on the observer's state of motion. General relativity, published a decade later, redefined gravity not as a force but as curvature of spacetime itself. These theories forced physics to abandon Newtonian concepts that had seemed self-evidently true, replacing them with a stranger, more subtle description of reality. Special relativity rests on two postulates. First, the laws of physics are identical in all inertial reference frames, meaning all reference frames moving at constant velocity relative to each other. You can't perform any experiment to determine absolute rest, only relative motion matters. Second, the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. This seemingly innocuous statement has profound consequences. If light speed is constant for all observers, space and time must be flexible. Consider a light pulse traveling from rear to front inside a moving train, as observed from the train and from the platform. From the train frame, the light travels the train's length at speed c. From the platform frame, during the time light travels, the train moves forward, so the light travels a longer distance. Yet both observers measure the same light speed. The only resolution is that time intervals and space intervals differ between frames. Time dilates, moving clocks run slow. Length contracts, moving objects shrink along their direction of motion. These effects aren't illusions or measurement artifacts. They are real features of spacetime structure. Time dilation has been confirmed with atomic clocks on airplanes and satellites, which show measurable time differences compared to ground clocks. Particle accelerators routinely observe particles traveling at near light speed, living much longer than they would at rest, exactly as relativity predicts. GPS satellites must account for both special relativistic effects from their motion and general relativistic effects from weaker gravity at their altitude or positions would drift meters per day. The relativity of simultaneity means events simultaneous in one frame aren't simultaneous in another. Two events happening at the same time according to one observer occur at different times according to an observer in relative motion. This isn't about signal delays, it's about the fundamental structure of spacetime. There's no absolute now extending across the universe. Simultaneity is frame-dependent just as position and velocity are. Mass and energy prove to be equivalent, related by Einstein's famous equation E=mc². Mass is a form of energy. Energy has mass. Rest mass can convert to other energy forms, as in nuclear reactions. The energy in a photon, which has zero rest mass, still has an equivalent mass and contributes to gravity. This mass-energy equivalence explains why light can't escape black holes and why gravitational lensing bends light paths. The gravitational field curves spacetime through which even massless photons travel. Nothing with mass can reach light speed. As objects accelerate, relativistic effects become important. Mass increases, time dilates, length contracts. Accelerating to light speed would require infinite energy. Light speed is a cosmic speed limit, and only massless particles like photons can travel at this speed. This doesn't mean faster than light travel is absolutely impossible. It means traveling through space at faster than light speed is impossible. Clever ideas like warp drives involve contracting space ahead and expanding it behind, perhaps allowing effective faster than light travel without locally exceeding light speed, though such solutions require exotic matter with negative energy density, and it's unclear whether they are physically realizable. General relativity extends special relativity to include acceleration and gravity. Einstein's key insight, the equivalence principle, states that gravitational and inertial mass are identical, meaning gravity and acceleration are locally indistinguishable. In a closed room, you can't tell whether you're standing on Earth's surface feeling gravity or in a spaceship accelerating at 1 g. This principle led Einstein to a radical reconception of gravity. Rather than being a force, gravity is the curvature of spacetime, caused by mass and energy. Mass tells spacetime how to curve, spacetime tells mass how to move. Planets orbit stars not because they are pulled by a force, but because they are following straight lines, called geodesics, through curved spacetime. A geodesic is the shortest path between points, analogous to great circles on Earth's surface representing shortest paths between locations. Free-falling objects follow geodesics, experiencing no proper acceleration, which is why astronauts feel weightless despite being well within Earth's gravitational field. Massive objects curve spacetime around them. Near a black hole, curvature becomes extreme. At the event horizon, spacetime curvature is so severe that all future directed paths point inward. Escape becomes impossible, even for light. Inside the event horizon, in some sense the roles of time and space swap. Moving forward in time inexorably carries you toward the singularity, just as outside the horizon, existing in time inevitably means existing in space. Gravitational time, dilation means time, passes more slowly in stronger gravitational fields. A clock on Earth's surface runs slightly slower than one at high altitude where gravity is weaker. For everyday heights, the effect is tiny but measurable with atomic clocks. Near a black hole's event horizon, time dilation becomes extreme. An outside observer watching something fall into a black hole would see it slow, dimming and red-shifting, asymptotically approaching but never quite reaching the horizon as its clock appeared to run ever slower. Gravitational waves are ripples in spacetime, curvature, predicted by general relativity and first detected in 2015. Accelerating masses produce gravitational waves much as accelerating charges produce electromagnetic waves, though gravitational waves are far weaker. The detected waves came from merging black holes over 1 billion light-years away, each tens of solar masses, in spiraling and colliding. The merger converted about 3 solar masses of mass energy into gravitational radiation in a fraction of a second, briefly outshining all stars in the observable universe combined, though in gravitational waves rather than light. The expanding universe is another prediction, or at least natural consequence, of general relativity. Einstein's equations relate spacetime, curvature to mass-energy distribution. Applying them to the entire universe requires assumptions about the universe's large-scale structure. The simplest assumption, reasonably accurate on the largest scales, is that the universe is homogeneous and isotropic, meaning the same everywhere and in all directions. With this symmetry, Einstein's equations predict that the universe must be expanding or contracting. A static universe is unstable. Observations confirm expansion. Distant galaxies are redshifted, their light stretched to longer wavelengths by the expansion of space itself during the light's journey. More distant galaxies have greater redshifts, showing they are receding faster, consistent with uniform expansion. Extrapolating backward, the universe was denser and hotter in the past, leading to Big Bang cosmology. The cosmic microwave background, discovered in 1965, is thermal radiation from the hot, dense early universe, now cooled by expansion to less than 3 Kelvin. Dark energy is a mysterious component that causes the universe's expansion to accelerate. Observations of distant supernova revealed this acceleration in the late 1990s, earning a Nobel Prize. Dark energy constitutes about 68% of the universe's total energy density, yet its nature remains unknown. It might be a cosmological constant, an energy density inherent to empty space itself, or something more exotic. Understanding dark energy is one of the most pressing questions in cosmology. Dark matter, distinct from dark energy, is matter that interacts gravitationally but not electromagnetically, making it invisible to telescopes. Its existence is inferred from gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxies in clusters move too fast to remain bound without additional mass, and gravitational lensing shows more mass than visible matter accounts for. Dark matter comprises about 27% of the universe's total energy, leaving only 5% for ordinary matter. What dark matter is remains unknown, though many candidates have been proposed. The quantum realm. Quantum mechanics describes nature at the smallest scales, where the classical physics of everyday experience breaks down. In the quantum realm, particles don't have definite positions until measured. They exist in superpositions of multiple states simultaneously. Identical particles are fundamentally indistinguishable. Measurement outcomes are inherently probabilistic, not predictable with certainty even with perfect information. These features seem bizarre from a classical perspective, yet quantum mechanics is the most accurate theory in science, its predictions confirmed to extraordinary precision across vast domains. The photoelectric effect, explained by Einstein in 1905, provided early evidence for light's particle nature. Shining light on metal surfaces can eject electrons, but the effect depends on light's frequency, not intensity. Classical wave theory predicted that brighter light, carrying more energy, should eject electrons more energetically, regardless of frequency. Instead, only light above a threshold frequency ejects electrons at all, and increasing intensity increases the number of electrons ejected but not their energy. Einstein explained this by proposing that light consists of particles, called photons, each carrying energy proportional to frequency. High-frequency photons carry enough energy to knock electrons free. Low-frequency photons don't, no matter how many. This work earned Einstein his only Nobel Prize. The double-slit experiment demonstrated light's wave nature even more dramatically. Light passing through two narrow slits creates an interference pattern on a screen, alternating bright and dark bands. This is precisely what waves do. The bands come from constructive and destructive interference between waves from the two slits. The stunning twist comes when reducing light intensity until only one photon passes through at a time. Each photon produces a single dot on the screen, as expected for a particle. But sending many photons, one by one, still builds up an interference pattern. Each photon somehow interferes with itself, passing through both slits simultaneously, yet always arriving at the screen as a localized particle. This wave-particle duality isn't specific to light. Electrons, atoms, even molecules display the same behavior. An electron passing through a double slit creates an interference pattern, behaving as a wave, yet it always arrives at the detector as a particle localized to a point. The wave describes probability amplitudes for where the particle might be found. Before measurement, the electron exists in a superposition described by a wave function spread through space. Measurement causes the wave function to collapse to a definite location, with probability determined by the wave function's magnitude squared at that point. Heisenberg's uncertainty principle quantifies a fundamental limit on precision. Certain pairs of properties, like position and momentum, or energy and time, cannot simultaneously have definite values. The product of their uncertainties is bounded below by Planck's constant divided by 4 pi. This isn't about measurement disturbing the system. It's an intrinsic feature of quantum mechanics. A particle doesn't have simultaneously exact position and momentum. The wave function can be sharply peaked in position, giving well-defined location but highly uncertain momentum. Or it can be sharply peaked in momentum, giving well-defined momentum but highly uncertain position. But it can't be sharply peaked in both. The uncertainty principle has profound implications. It explains why atoms are stable. Classical physics predicts electrons orbiting nuclei should radiate electromagnetic energy and spiral inward in a fraction of a second, making atoms collapse. Quantum mechanically, confining an electron very close to the nucleus makes its momentum highly uncertain, giving it substantial kinetic energy. The lowest energy state balances attraction to the nucleus against kinetic energy from confinement, keeping the electron in a stable orbital, a region where it's likely to be found, but not a classical trajectory. Quantum superposition means a system can exist in multiple states simultaneously until measured. Schrödinger's cat, a thought experiment, illustrates this strangeness. A cat in a box has its fate linked to a quantum event, perhaps radioactive decay detected by a Geiger counter that triggers a poison release. Quantum mechanically, until the decay is observed, the radioactive nucleus exists in a superposition of decayed and not decayed states. If we take quantum mechanics at face value, the entire system, including the cat, is in a superposition of dead and alive until someone opens the box and observes. The cat is genuinely neither alive nor dead, but both until observation collapses the superposition. This seems absurd for macroscopic objects like cats. The resolution involves decoherence. Quantum superpositions are fragile, easily disrupted by interaction with the environment. A cat interacts with countless air molecules, photons, and so on. These interactions constantly measure the cat, destroying superposition nearly instantly. Macroscopic objects effectively collapse their own wave functions through environmental interaction, which is why we don't observe quantum superposition for everyday objects. Maintaining quantum superposition requires isolation from the environment, which is extraordinarily difficult for anything larger than microscopic. Quantum entanglement creates correlations between particles stronger than classically possible. When two particles interact and then separate, their quantum states can remain correlated even across large distances. Measuring one particle's state instantly determines the other's, regardless of separation. Einstein called this spooky action at a distance, thinking it showed quantum mechanics incompleteness. But experiments have confirmed entanglement's reality. It doesn't allow faster than light communication because measurement outcomes are random. You can't control what result you get, so you can't send information. But the correlations violate classical limits, proving quantum mechanics truly describes nature. Quantum mechanics successfully explains atomic and molecular structure. Electrons in atoms exist in orbitals, regions where they are likely to be found, characterized by quantum numbers. The periodic table's structure follows from quantum rules governing how electrons fill orbitals. Chemical bonds form through orbital overlap, sharing or transferring electrons between atoms. All of chemistry, and thus biochemistry and life, ultimately rests on quantum mechanical principles governing electron behavior. Quantum field theory extends quantum mechanics to fields, creating a framework that combines quantum principles with special relativity. In quantum field theory, particles are excitations of underlying fields. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Particles can be created or destroyed. What's conserved is charge, energy, momentum, and other quantum numbers. This framework underlies the standard model of particle physics, which describes all known particles and 3 of the 4 fundamental forces with remarkable accuracy. The standard model includes matter particles, fermions, which make up the substance of ordinary matter, and force carrier particles, bosons, which mediate interactions. Fermions include quarks, which combine to form protons and neutrons, and leptons, including electrons and neutrinos. Bosons include photons carrying electromagnetic force, gluons carrying the strong nuclear force, W and Z bosons carrying the weak nuclear force, and the Higgs boson, whose associated field gives particles mass. Gravity isn't included. Incorporating it remains an open problem. Quantum tunneling allows particles to pass through barriers they classically couldn't surmount. A particle encountering a potential barrier has some probability of appearing on the far side even if it doesn't have enough energy to go over. The wave function doesn't abruptly drop to 0 at the barrier, it decays exponentially through the barrier, giving non-zero amplitude on the far side. This phenomenon enables nuclear fusion in stars, radioactive decay, and the operation of scanning tunneling microscopes that image individual atoms. Tunneling probabilities decrease exponentially with barrier thickness and height, making it negligible for macroscopic objects, but significant for quantum particles. The architecture of atoms. The atom, once thought to be indivisible, as its name suggests, reveals itself to be a miniature cosmos, a system of particles bound by forces into structures that determine all material properties. Understanding atomic architecture opened the door to explaining chemistry, developing new materials, and manipulating matter at its most fundamental levels. The nuclear model of the atom emerged from Ernest Rutherford's gold foil experiment in the early 20th century. Shooting alpha particles at thin gold foil, most passed straight through, but occasionally one bounced back at large angles. This shocked Rutherford, who compared it to firing artillery shells at tissue paper and having some rebound. The only explanation was that most of the atom is empty space, with almost all its mass concentrated in a tiny, dense nucleus. Later work revealed the nucleus contains protons, positively charged, and neutrons, electrically neutral but with similar mass to protons. Electrons, nearly 2,000 times lighter than protons, occupy the vast space surrounding the nucleus. In the classical picture, they orbit like planets around the Sun, but classical physics predicts orbiting electrons should radiate energy and spiral into the nucleus almost instantly. This doesn't happen because quantum mechanics forbids it. Electrons exist in orbitals, three-dimensional regions around the nucleus with varying probabilities of finding the electron. These orbitals have discrete energy levels. Electrons can only possess certain specific energies, not any arbitrary value. The hydrogen atom, with one proton and one electron, is the simplest atom and the only one for which Schrödinger's equation can be solved exactly. The solutions give orbitals labeled by quantum numbers. The principal quantum number specifies the electron's energy level and roughly its distance from the nucleus. The angular momentum quantum number determines the orbital's shape, spherical for s orbitals, dumbbell-shaped for p orbitals, more complex for d and f orbitals. The magnetic quantum number specifies orbital orientation, and the spin quantum number describes the electron's intrinsic angular momentum, which despite its name doesn't represent physical spinning but is a quantum property with no classical analog. The Pauli exclusion principle, one of quantum mechanics' most important rules, states that no two fermions can occupy the same quantum state. Since electrons are fermions, no two electrons in an atom can have identical quantum numbers. This principle structures the periodic table. The first electron occupies the lowest energy orbital. The second joins it with opposite spin. The third must go to the next higher energy orbital, and so on. As atoms gain more electrons, they fill orbitals following well-defined patterns that repeat periodically, which is why elements in the same column of the periodic table have similar chemical properties. Chemical bonds form when atoms share or transfer electrons, seeking stable electron configurations, usually complete outer shells. In covalent bonds, atoms share electrons, with shared pairs forming bonds between nuclei. The strength and number of bonds an atom can form depends on its electron configuration. Carbon, with 4 electrons in its outer shell, can form 4 bonds, allowing it to create the complex molecules essential for life. In ionic bonds, atoms transfer electrons, creating positive and negative ions that attract electrostatically. In metallic bonds, electrons move freely through a lattice of positive ions, explaining metals' electrical conductivity and other properties. The spectrum of light emitted or absorbed by atoms reveals their internal structure. When an electron jumps from a higher energy level to a lower one, it emits a photon with energy equal to the level difference. Since energy levels are quantized, photon energies are quantized too, producing discrete spectral lines rather than continuous spectra. Each element has a unique pattern of spectral lines, a kind of fingerprint. Astronomers identify elements in distant stars by analyzing their spectra, determining not just composition but temperature, density, and motion through Doppler shifts. Quantum mechanics explains the periodic table's structure and thus chemical behavior. Elements in the same group have similar outermost electron configurations, leading to similar chemistry. Noble gases have full outer shells, making them chemically inert. Alkali metals have 1 electron beyond a full shell, which they readily lose, forming positive ions. Halogens need 1 electron to fill their outer shell, eagerly accepting electrons and forming negative ions. Transition metals have partially filled inner shells, giving them complex chemistry with variable oxidation states and often colorful compounds. Isotopes are atoms of the same element with different numbers of neutrons. They have identical chemical properties since chemistry depends on electrons and number of protons, but different physical properties like mass and nuclear stability. Carbon-12 has 6 neutrons, carbon-14 has 8. Carbon-14 is radioactive, decaying with a half-life of about 5,700 years, which makes it useful for dating organic materials up to tens of thousands of years old. Radioactivity occurs when unstable nuclei spontaneously transform, releasing energy and particles. Alpha decay emits helium nuclei, 2 protons and 2 neutrons bound together. Beta decay converts a neutron to a proton or vice versa, emitting an electron or positron and a neutrino. Gamma decay emits high-energy photons. The decay rate follows exponential laws. After one half-life, half the original nuclei have decayed. After 2 half-lives, 3/4 have decayed, and so on. Different isotopes have half-lives ranging from fractions of a second to billions of years. Nuclear forces bind protons and neutrons into nuclei. The strong nuclear force, one of nature's 4 fundamental forces, operates over very short ranges, roughly the size of nuclei, but is much stronger than electromagnetism at those distances. It acts between quarks, within protons and neutrons, and also between neighboring nucleons. Without the strong force, electrostatic repulsion would blow nuclei apart. Nuclei larger than lead are typically unstable because the strong force's short range means distant nucleons don't bind as effectively, while electromagnetic repulsion acts over all distances. Nuclear binding energy is the energy needed to disassemble a nucleus into individual protons and neutrons. It's also the energy released when those nucleons assemble into a nucleus. Binding energy per nucleon varies with atomic number, reaching a maximum around iron. This curve explains both nuclear fission and fusion. Splitting heavy nuclei like uranium releases energy because the fission products have higher binding energy per nucleon. Fusing light nuclei like hydrogen releases energy for the same reason. Iron is at the peak. Fusing or fissioning iron nuclei requires energy input rather than releasing it. Nuclear fusion powers stars. In the sun's core, hydrogen fuses to helium through a multi-step process, releasing energy that ultimately reaches us as sunlight. Fusion requires extremely high temperatures and pressures to overcome electrostatic repulsion and bring nuclei close enough for the strong force to bind them. In massive stars, when hydrogen is exhausted, helium fuses to carbon and oxygen. More massive stars proceed through further stages, fusing carbon to neon and magnesium, neon to oxygen and magnesium, oxygen to silicon and sulfur, and finally silicon to iron. Each stage releases less energy and runs faster than the previous one. When a massive star's core becomes iron, fusion stops producing energy. Without fusion's outward pressure to balance gravity, the core collapses catastrophically in less than a second, rebounding in a supernova explosion that can briefly outshine an entire galaxy. The explosion scatters heavy elements through space, enriching the interstellar medium. Elements heavier than iron are created in supernova and neutron-star mergers formed through rapid neutron capture in these extreme environments. The golden jewelry, the uranium in power plants, even the selenium and iodine essential for life, were all forged in such cosmic explosions. Quantum chromodynamics, the theory of the strong force, describes quarks and gluons. Quarks come in 6 types, called flavors: up, down, charmed, strange, top, and bottom. Protons consist of 2 up quarks and 1 down. Neutrons have 1 up and 2 down. Quarks carry a property called color charge, analogous to electric charge but with 3 types rather than 2. Gluons are the strong force carriers, mediating interactions between quarks. Unlike photons, which don't carry electric charge, gluons carry color charge, allowing them to interact with each other as well as with quarks. A remarkable property of the strong force is confinement. Quarks are never observed in isolation, they only exist bound in composite particles. Trying to pull quarks apart requires ever-increasing energy. At some point, there's enough energy to create new quark-antiquark pairs which instantly bind to the separating quarks, preventing isolation. This is why matter appears to be made of protons, neutrons, and other composite particles, not free quarks. Antimatter consists of antiparticles with the same mass as ordinary particles but opposite charge and other quantum numbers. An electron's antiparticle is the positron, identical except for positive charge. When a particle meets its antiparticle, they annihilate, converting their mass energy completely to photons or other particles. The universe's apparent lack of antimatter, despite physics equations treating matter and antimatter symmetrically, is a major, unsolved problem. The Big Bang should have created equal amounts, yet nearly everything we observe is matter. Some asymmetry in fundamental physics must have caused a slight matter excess, allowing matter to dominate after most of it annihilated with antimatter in the early universe. The fabric of spacetime, space, and time form an integrated four-dimensional structure called spacetime. This unity, revealed by special relativity, becomes even more profound in general relativity, where spacetime's geometry is dynamic, shaped by and shaping the distribution of matter and energy. Understanding spacetime's nature requires abandoning intuitive notions from everyday experience and embracing a more abstract, mathematical view. In Newtonian physics, space and time are separate and absolute. There's a universal now, extending throughout space, and distances and durations are the same for all observers. Special relativity shattered this picture. Events that are simultaneous for one observer occur at different times for an observer in relative motion. Space and time mix together under changes of reference frame, like how x and y coordinates mix under rotations. The appropriate framework isn't separate three-dimensional space and one-dimensional time, but four-dimensional spacetime. Minkowski diagrams visualize special relativity by plotting space horizontally and time vertically. Each point represents an event, something happening at a particular location and time. A particle's history traces a world line through spacetime, a curve connecting all events that particle experiences. Light, traveling at the ultimate speed, traces world lines at 45-degree angles if we choose units where light speed equals 1. Nothing with mass can have a world line tilted more than 45 degrees, as that would require faster than light travel. The interval between two events in spacetime is a quantity all observers agree on, analogous to distance in ordinary space being the same regardless of coordinate rotation. The spacetime interval combines time difference and space distance in a specific way, with time contribution entering with opposite sign compared to space. For light rays, the interval is 0. Time and space contributions exactly cancel. For time-like separated events, like two events in your life, the interval is positive and represents the proper time elapsed on a clock moving between the events. For space-like separated events, occurring too far apart in space and too close in time for light to connect them, the interval is negative. Causality relates to spacetime structure. An event can only causally affect other events in its forward light cone, the region of spacetime reachable by signals traveling at or below light speed. Events in the backward light cone could have affected the event in question. Events outside both cones are space-like separated. No causal connection is possible. Different observers may disagree on time ordering for space-like separated events, but they always agree on time ordering for time-like separated events, preserving causality. Cause always precedes effect in all reference frames for events that can be causally connected. General relativity describes gravity as spacetime curvature. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. Einstein's field equations 10 coupled nonlinear partial differential equations relate spacetime curvature at each point to the stress-energy tensor, which describes matter and energy distribution. These equations are extraordinarily complex. Exact solutions exist only for highly symmetric situations like spherical stars or black holes. The Schwarzschild solution describes spacetime around a non-rotating spherical mass like a star or black hole. Far from the mass, spacetime is nearly flat, and Newtonian gravity is accurate. Closer in, curvature effects become important. Clocks run slower, lengths contract, and light bends more than Newtonian gravity predicts. At the Schwarzschild radius, twice the mass times Newton's gravitational constant divided by light speed squared, something remarkable happens. This radius defines the event horizon. For most objects, the Schwarzschild radius is deep inside them. For the Sun, it's about 3 kilometers, well inside the solar surface. But if mass compresses within its Schwarzschild radius, it becomes a black hole. Black holes are regions where spacetime curvature becomes so extreme that escape is impossible. At the event horizon, the escape velocity reaches light speed. Inside, all trajectories lead inexorably inward toward the singularity at the center, where classical general relativity predicts infinite curvature and breaks down, signaling the need for a quantum theory of gravity. Anything crossing the event horizon is doomed, but from an outside perspective, it never quite arrives. Time dilation becomes infinite at the horizon, so distant observers see infalling matter slow asymptotically, freezing at the horizon, never seeing it cross. Rotating black holes, described by the Kerr solution, are more complex. They drag spacetime around with them, a phenomenon called frame dragging. Near a rotating black hole, nothing can remain stationary. Everything must rotate in the same direction as the hole. The event horizon is surrounded by an ergosphere where this effect is strong. It's possible in principle to extract energy from a rotating black hole by dropping matter into the ergosphere, where it can gain energy from the hole's rotation before escaping. Wormholes are hypothetical spacetime structures connecting distant regions, shortcuts through spacetime. Einstein's equations allow wormhole solutions, but they require exotic matter with negative energy density to hold them open. Whether such matter can exist and whether wormholes can form naturally or be constructed is unknown. Even if wormholes exist, using them for travel might be impossible due to instabilities or other issues. The expanding universe represents spacetime itself stretching, increasing distances between galaxies. Galaxies aren't moving through space away from each other in the usual sense. Rather, space between them expands, carrying them apart. This expansion is described by the scale factor in cosmological models, which quantifies how distances grow with time. Hubble's law states that recession velocity is proportional to distance, a natural consequence of uniform expansion. The Hubble constant quantifies the current expansion rate. The Big Bang wasn't an explosion in pre-existing space, but the expansion of spacetime itself from an initial hot, dense state. Asking what happened before the Big Bang is tricky because time itself began with the Big Bang in standard models. If spacetime is finite in the past, asking about before is like asking what's north of the North Pole. Some models allow time to extend before the Big Bang, perhaps with a contracting phase or a bounce from a previous universe, but these are speculative. Cosmic inflation, a brief period of exponential expansion very early in the universe's history, explains several cosmological puzzles. It explains why the universe is so flat, so uniform, yet has tiny density fluctuations that seeded structure formation. Inflation stretched a tiny, causally connected region to enormous size, making the observable universe a minuscule fraction of the whole explaining uniformity. Quantum fluctuations during inflation were stretched to macroscopic scales, providing the seeds for galaxies and cosmic structure. The ultimate fate of the universe depends on its contents and geometry. With only matter and radiation, expansion would eventually slow and possibly reverse, leading to a big crunch. With a cosmological constant, or dark energy, expansion continues forever, even accelerating. Given current measurements suggesting dark energy dominates, the universe appears headed for eternal expansion. Galaxies outside our local group will eventually recede beyond the cosmic light horizon, disappearing from view. Stars will exhaust their fuel, leaving only black holes which eventually evaporate via Hawking radiation over unimaginably long timescales, leaving a cold, dark, empty universe approaching maximum entropy. The symphony of science. As we drift toward the close of this exploration, it's worth stepping back to appreciate the extraordinary tapestry, to borrow the word one last time, that science has woven. Each concept we've touched upon tonight, from the fundamental nature of motion to the quantum weirdness underlying reality, from the flow of heat to the curvature of spacetime itself, represents a thread in a far larger pattern. These threads interweave, support one another, and create a coherent picture of the natural world that is both humbling and empowering. The unity underlying physical law reveals itself at many levels. The same principles of energy conservation that explain a ball rolling down a hill also govern the most violent cosmic explosions. The electromagnetic forces binding atoms into molecules create the material world we inhabit, from solid rock to flowing water to the very proteins that make life possible. The quantum mechanics that seemed so strange and abstract is absolutely necessary to explain why matter is stable, why chemistry works, why stars shine. What's perhaps most remarkable about physics is its predictive power. From a handful of principles and a few measured constants, we can predict phenomena never before observed, sometimes in stunning detail. General relativity predicted gravitational waves a century before technology advanced enough to detect them. Quantum mechanics predicted antimatter vacuum fluctuations and countless other phenomena confirmed by experiment. The Standard Model of particle physics predicted the Higgs boson's existence and properties decades before the Large Hadron Collider finally discovered it. This predictive success reflects something deep about reality. The universe operates according to comprehensible rules expressible in mathematical language. Those rules are consistent across vast ranges of scale, energy, and time. The same quantum mechanics governing electrons in atoms governs behavior of quarks in protons, behavior of photons in light, behavior of entire superconducting circuits. The same relativity describing spacetime around Earth applies to neutron stars, black holes, and the universe's large-scale structure. Yet, for all we've learned, vast mysteries remain. We don't know what dark matter is, what constitutes most of the universe's mass. We don't know the nature of dark energy driving cosmic acceleration. We haven't unified quantum mechanics with general relativity into a complete theory of quantum gravity. We don't fully understand how complexity and life emerge from fundamental physics. We don't know whether our universe is unique or part of a larger multiverse, whether physical constants could have been different, whether life and consciousness are inevitable or wildly improbable flukes. These open questions keep physics vital and exciting. Each answer raises new questions. Each solved mystery reveals deeper puzzles. The history of physics is a story of successive approximations, each more accurate and more general than the last. Newtonian mechanics gave way to relativity and quantum mechanics, but Newton's laws remain excellently accurate for everyday conditions. Quantum field theory might someday be subsumed into string theory or some other framework, but its predictions won't become wrong, merely special cases of something more general. This pattern suggests that we'll never reach a final theory of everything, that each level of understanding opens windows to deeper levels. And perhaps that's as it should be. The joy of science isn't just in the answers, but in the process of discovery, the excitement of solving puzzles, the satisfaction of understanding something previously mysterious. A universe completely understood might be less interesting than one full of mysteries waiting to be unraveled. For those seeking sleep, perhaps there's comfort in these scientific concepts. The universe operates according to laws, not capriciously but with consistency and regularity. The same sunrise that greeted humans 10,000 years ago operates on the same principles as today's sunrise. The atoms in your body are governed by the same quantum mechanics as atoms anywhere in the universe. There's an orderliness underlying apparent chaos, patterns within complexity, predictability within uncertainty. The scientific worldview offers a kind of secular spirituality, a sense of connection to something larger. The carbon in your cells was forged in stars. The oxygen you breathe was produced by plants through photosynthesis powered by nuclear fusion in the sun. The iron in your blood was created in supernova explosions. You're literally made of stardust, your substance created in the cosmos and assembled over billions of years through physical and chemical processes into the conscious being experiencing this moment. Every breath you take involves quadrillions of molecules following quantum mechanical rules, exchanging energy, facilitating the chemistry of life. Every heartbeat is powered by electrical signals and chemical gradients, ultimately traceable to electromagnetic forces between electrons and nuclei. Every thought you think emerges from neural activity involving ion flows, neurotransmitter release, and countless molecular interactions, all governed by physical law. Yet somehow, from these unintelligent fundamental constituents following simple rules, consciousness arises. The universe has become aware of itself through us. Matter has organized itself into patterns capable of contemplating matter. This emergence of mind from mindless substance remains one of the deepest mysteries, sitting at the intersection of physics, chemistry, biology, and philosophy. Science doesn't claim to answer every question. It has nothing to say about purpose or meaning, about aesthetics or ethics, except insofar as those emerge from physical substrates in brains. It describes how things work, not why they exist or what they mean. But within its domain, science provides unparalleled insight into nature's workings. It gives us tools to manipulate our environment, curing diseases, building technologies, expanding our capabilities. It reveals beauty in natural phenomena, from the symmetric patterns of snowflakes to the vast spiral structure of galaxies. It connects us to the deep history of the cosmos and to all life on Earth through our shared evolutionary heritage. The concepts we've explored tonight represent a small fraction of scientific knowledge, themselves simplified for accessibility. Behind each concept lies mathematical machinery of varying sophistication, from basic algebra to exotic topology. Each statement about nature rests on foundations of experimental evidence, sometimes from centuries of careful measurement and observation. Scientists didn't simply think up these ideas. They were forced to these conclusions by nature itself, by patterns in data that demanded explanation. The scientific method, that process of hypothesis, prediction, experiment, and revision, has proven remarkably successful at expanding knowledge. It's self-correcting. Wrong ideas eventually get weeded out when predictions fail. It's cumulative. Each generation builds on previous work. It's collaborative. Thousands of scientists worldwide contribute pieces to our collective understanding. And it's open. Anyone can in principle check anyone else's work, replicate experiments, verify claims. This doesn't mean science is perfect or that scientists never make mistakes. They do frequently. But the system tends toward truth over time as errors are caught and corrected. The picture of nature that emerges from this process is contingent, always potentially subject to revision, yet increasingly confident. We're more certain of quantum mechanics and relativity than we are of Newtonian mechanics, not because Newton was wrong, but because we've tested modern theories far more extensively. As you let these ideas settle in your mind, you might notice how they connect to direct experience. The warmth you feel is molecular kinetic energy. The light allowing you to see originates from electronic transitions or thermal radiation. The solidity of objects arises from electromagnetic forces and the Pauli exclusion principle. The passage of time relates to entropy increase. The pull of gravity emerges from spacetime curvature. Every physical sensation, every observation, ties back to fundamental principles. Perhaps that connection between abstract physics and lived experience is the most valuable takeaway. Science isn't some arcane body of knowledge accessible only to specialists. It's a description of reality, your reality, the world you inhabit and experience every moment. Understanding physics doesn't remove wonder, it deepens it. Knowing that stars are fusion reactors doesn't make them less beautiful. Understanding how eyes and brains process light doesn't diminish the glory of a sunset. Recognizing that consciousness emerges from neural dynamics doesn't make subjective experience less real or less meaningful. If anything, scientific understanding amplifies appreciation. The night sky becomes more awe-inspiring when you realize you're looking back in time, that light from distant galaxies left them millions or billions of years ago, that those galaxies contain billions of stars, each potentially harboring planets, that the same physical laws govern them as govern Earth. A forest becomes more marvelous when you understand the complex chemistry of photosynthesis, the quantum mechanics allowing chlorophyll to capture light energy, the ecological networks linking every organism. The universe revealed by science is far stranger and more wondrous than any mythology. Quantum mechanics alone provides enough weirdness to boggle minds, particles in multiple places simultaneously, observation affecting reality, entangled particles linked across arbitrary distances, virtual particles winking in and out of existence in empty space. Relativity adds time dilation, length contraction, mass-energy equivalence, curved spacetime, black holes from which nothing escapes. Cosmology provides a universe born in a Big Bang, expanding for almost 14 billion years, containing hundreds of billions of galaxies, each with hundreds of billions of stars, most of it composed of mysterious dark matter and dark energy. This is the universe we inhabit, revealed through patient observation, clever experiment, and mathematical reasoning. It's a universe governed by comprehensible laws, yet full of surprise and mystery. It's a universe that gave rise to us, conscious beings capable of understanding our own existence and origin at least partially. That alone seems miraculous, that the universe should become conscious of itself, that matter should organize into patterns capable of contemplating matter. And now, as your mind begins to quiet, as the concepts we've discussed drift into the background, perhaps becoming material for dreams, remember that you're part of this grand cosmic story. You're an expression of the universe's complexity, of its capacity for self-organization and consciousness. The atoms in your body have existed for billions of years, cycling through stars and planets, through air and water, through countless organisms. They've been temporarily assembled into the pattern that is you, animated by energy flowing through metabolic networks, organized by information encoded in DNA molecules. You are stardust contemplating stars. You are the universe examining itself. And in this quiet moment, as you rest, the same physical laws that govern galaxies govern your breathing, your heartbeat, the neural activity underlying your fading thoughts. The conservation of energy ensures that while forms change, nothing is truly lost. The increase of entropy gives time its direction, but also enables the complexity that makes life possible. Quantum mechanics provides the stability of atoms and the unpredictability that might allow free will. Electromagnetism binds your body together and transmits sensory information about the world. The concepts of physics, vast and intricate as they are, all operate right here, right now, in and around you. They are not distant abstractions, but the very fabric of your existence. Rest in that knowledge. Find comfort in the universe's regularity, in the reliability of physical law, in the connection between yourself and the cosmos. Your home in this universe. You belong here. You're made of it, shaped by it, part of it. Sleep well, knowing that while you rest, the universe continues its eternal dance. Atoms vibrate. Molecules collide. Energy flows. Electromagnetic waves propagate. Spacetime curves. Quantum fields fluctuate. The laws of physics operate continuously, reliably, beautifully, governing everything from the quantum foam of spacetime itself to the largest structures in the cosmos. And you, briefly, are here to witness and understand a small part of it. That understanding is a gift, hard-won through centuries of human effort, enabled by curiosity and reason, by willingness to question and to follow evidence wherever it leads. It's a gift freely available to anyone willing to learn, to think, to wonder. The universe has secrets still, mysteries aplenty remaining to be solved. But it has also revealed much, and what it has revealed is extraordinary. As your consciousness dims and sleep approaches, let these ideas provide a gentle current carrying you into dreams. Dream of atoms and stars, of waves and fields, of time and space woven into a unified fabric. Dream of the quantum realm, where particles dance in superposition, of relativistic speeds, where time dilates and space contracts, of the expanding universe carrying galaxies ever farther into the cosmic night. Dream of the physical principles that make existence possible, the conservation laws and symmetries underlying nature, the forces binding matter and radiating through space. The science we've explored tonight is just a beginning, an introduction to deeper understanding waiting for those who pursue it. But even this glimpse reveals the profound beauty and elegant simplicity underlying nature's apparent complexity. A few principles, properly understood, illuminate vast territories of phenomena. A handful of forces and particles suffice to build everything we see. The same laws apply everywhere and everyone, making the universe noble despite its immensity. Rest now, and if you found value in this exploration, consider liking this video, subscribing to the channel for more journeys through scientific landscapes, and sharing this with others who might appreciate a different kind of bedtime story. One where the wonders are real, the mysteries genuine, and the beauty mathematical. Where understanding doesn't diminish marvel, but deepens it. Where knowledge connects us to the universe in ways both intellectual and visceral. The cosmos awaits further exploration. The laws of physics continue operating whether we understand them or not. But understanding enriches experience, transforms the ordinary into the extraordinary, reveals the hidden unity underlying nature's diversity. That's the gift of science, freely given to anyone willing to receive it. Sleep well in this amazing universe. Dream of the dance of particles and fields, of curved space-time and quantum superposition, of energy flowing through intricate patterns, of a cosmos stranger and more wonderful than imagination alone could conjure. Good night, and may your dreams be filled with the quiet beauty of scientific understanding.